Hello everyone, and welcome to Tap It, Shake It, Fling It, Chip It, the gesture animation dance. For those who don't know me, my name is Nicole Terc. I'm an Android GDE and also a tech lead at HoopSpot. And you can find these ramblings and much other things in my... Oh, why is not updating? Yeah. It's showing here, but not there. No, it's there. Cool. As I was saying, my name is Nicole Terc, and you can find this and more ramblings at that GitHub profile. But with this out of the way, there you go, it's working now, thank you. Let's go over what are we going to be doing today. And the answer to that is, of course, we're going to be making some dancing chip. And in order to make this dancing chip, we're going to be using three things. We're going to be using animations, we're going to be using gestures, and we're going to be using sensors. But in order to see how these three things are going to be meshing together, let's jump over our chip strategy of the day, which is going to be pretty straightforward, don't worry. The only thing we're going to do is we're going to grab some gestures, we're going to grab some sensors, and getting the data from those two, we're going to be creating some fun animations. Or at least, I think they're fun. And because I wanted to challenge myself, we're going to be doing all of this using Kotlin multi-platform. So let's jump into it, and let's get a closer look at each of these three blocks. And let's start with animations. And the part I want us to focus about in animations is actually, how do you actually make animations? Whenever I find myself in this step of the process, I usually answer three questions, which are what, when, and how. What properties do I want to animate? Do I want to change the color? Do I want to change the scale? Do I want to change whatever I can add in my views? When am I going to be changing them? Do I want to change them when I tap a button, when I swipe in the screen? And how am I going to be changing them? Am I going to use toggling from one value to the other? Am I going to just change colors or whatever I want? Once I'm finished these three translations to code, I usually add a 4 optional step, which is basically just play around, see what happens, and have some fun with these animations. Cool. But what are we actually going to use to make these animations? The answer is some animation APIs. If you haven't taken a look at the Jetpack Compose animation APIs documentation, I highly recommend that you do so. Part of all the documentation of each of the APIs, you're going to find this trusty flowchart that is going to help you pick up the right animation API for you. Don't worry, I know it looks daunting, but it's pretty easy. You just start from the start, go over the nice little branches until you find the use case of your scenario, and right there, you're going to find the API you need to use, which in our case, since we're going to be playing with gestures, is the animatable API. Now, this animatable API is a coroutine-based API. I'm not going to be going super deep on this. We're just going to see how to use it. But with this, I think we're done with animations. We should be ready. So let's start dancing. Why is it not updating again? Oh, there it is. Yes, small disclaimer. This chip is actually a canvas, which is not showing there. What is happening? It's not updating, folks. Let me just unplug. Plug again. Let's wait for a second. There you go. As I was saying, this chip is actually a canvas, which is an out-of-the-box composable. So everything you're going to see here, you can replicate with your favorite composable, like a box or an image or text or whatever you want. In my case, I'm going to stick with the chip because you know it's already in the name. So as I was saying, let's dance. And let's start with some gesture moves. And just for our first dance step, let's go for a classic. Tap to scale. As I said before, in order to start this animation, we're just going to answer our three questions. What, when, and how. In this case, we're going to be changing the scale of the chip, when I'm tapping on it, and how I am just going to toggle from 1 to 1.2. Why these numbers? Because I like them. There is no underlying meaning about this. So let's translate this into code. It's working, cool. If you start your implementation for taps to scale, you will end up with something like this. Oh, it looks a little bit tiny. I hope you can see it on the back. If not, I'm happy to share this after the talk. So the first thing we need to do is we need to define the scale of our chip as a value. Then we're just going to pass this value into our graphic layer composable chip. Important thing in here, whenever you're working with animations, make sure that you're using lambda-based modifier versus the regular one. This is just because you want to avoid recompositions, and this is the way to do so. Once you define the scale of the chip, the next step is, since we're going to be tapping on the chip to change things, we're going to just add a clickable modifier, and on that click, whenever someone clicks on it, we're just going to toggle the scale and change it. That's it, right? I hope nothing here is too surprising to anybody. And with this, we already have a tap-to-scale chip. But there's a glaring issue in this, and that is that we're actually not animating anything yet. So let's fix that. Since we said we're going to be using the animatable API, the only thing we need to do is, in that scale, instead of defining it as a float, we're going to define it as an animatable. You need to wrap it in a remember, you're just setting the value again, and since now it's an animatable, instead of just setting the value straight away, we're going to call the helper function animate2. And since it's a coroutine, we need to wrap it in a coroutine. And just with that, changing a couple of lines to something I already had, there you have it, an animated tap-to-scale chip. Cool, right? So now you have no excuses to start adding animations in your code. But this looks still a bit bland. Let's have some fun with it. Whenever I reach this step, I usually just beeline to animation spec. Animation spec is an optional property you can send in most of these animatable APIs, and this is basically just going to describe how the animation is going to play. I'm not going to go super deep in here. The only thing you need to know is that a lot of them are already out of the box, and you just basically need to use them. But just for the sake of seeing some of them, these are 3 of the ones I usually use. We have Twin, which is a time-based animation spec. We have Spring, which replicates that springy bounciness of a spring. And we have keyframes, one of my favorites, which basically lets you set the keyframes of an animation that the animation needs to hit when it is animating. Whew, so much animation words. But enough of this. Let's go back to our example, and let's see how to use this. As I said, I'm going to define the animation spec, so the only thing I need to do is create it. In this case, I'm setting a spring that is really bouncy, but also is really stiff. And with just this property change, you have a totally different tap-to-scale chip. And following this same approach at this, you can just change the animation spec and end up with really different animations. So if you want to just add a little twist of funniness of your animations, just go to animation spec, play around until something looks cool, and that's it. But for now, I think that's it for tap-to-scale. Let's jump into the next step, reposition. Because it seems that just standing in place is not a correct dance strategy. So let's make our chip move too. Again, we're going to answer our 3 questions, what, when, and how. In this case, we're going to be changing the position. We're going to be changing it whenever there's a drag gesture in our chip. And we're basically just going to be moving the chip wherever the finger is going. So let's translate this again into code, which would look like this. Again, first step is defining the property I'm animating. In this case, is translation, which, by the way, translation is basically the difference from the origin position of the chip and where you have it. So that's where we're going to be animating. And you may notice that this animatable looks a bit different. In this case, it's because I'm defining translation as an offset. And offset doesn't have an out-of-the-box animatable constructor. So in order to use an offset as an animatable, I need to pass also vector converter. Don't worry, I'm still not building anything. All of this is out of the box. The only thing you need to remember is that if you're creating an animatable and Android Studio complains, just check if there's already a vector converter you can use in order for your animatable to work. Cool. Once we have the translation, we're again defining this on the graphics layer. And in order to start listening to this dragging behavior, the only thing I need to do is add a draggable to the modifier. This is already going to contain all the logic, all the complicated maths, and everything to calculate this dragging behavior. The only thing we need to pass is a draggable state. That is basically going to be the way for me to tell my code how to react to this dragging behavior. which in our case is basically just going to update our translation. Important thing in here is that you may have seen, if you're in the front of the rows, that I'm using a snap to instead of animate to in this case. And that is because I don't want to actually animate the movement of my chip when my finger moves, because I don't want any delay from my finger moving and my chip following. So whenever you find yourself in this scenario, you want to use a snap to, which is basically going to ignore any animation spec, any animatables, and then just jump right into the value. It's kind of like the no animation animation. Cool. And now we have that, and we use this code, literally copy-pasted from our repository. You already have a dragon chip. Cool. But I think that's enough for this. You can, of course, play a little bit with animation specs, which could be a little bit complicated because you don't want any delay. But for now, I think that's it for reposition. Let's jump into a more interesting step. Fling and back. Again, as I said, answering our questions. In this case, I'm again changing position. But now I want to react to a fling gesture. If you don't know what a fling gesture is, basically it's a gesture when you're scrolling on a list, which is, I hope everyone has done in their Android device. And when you lift your finger and the list just scrolls and overshoots, that's a fling. So I want to listen to that, and now I want my chip to react to it. If the fling happens and my chip would end up inside the screen, I want it to just move there. But if my chip would end up outside the screen, I want it to move back to the center. Cool, right? So again, let's translate this into code. We're going to start with our draggable 2D step already. And the only thing we need to change in order to react to fling is instead that draggable 2D modifier, we're going to pass the optional parameter on drag stopped. This lambda is going to trigger whenever the finger leaves the screen, so I don't need to worry again about calculating this velocity or whatever. It's already done for me. I just need to react to it. So let's see how this fling move will look like. And it will look like this. I know it's a lot of code, and it may look a little bit tiny, but let's break it down. The first step is we need to calculate the target offset of my chip, which is a lot of words to just saying, like, I need to know where in my screen will my chip end up if I just let it fling. And in order to do that calculation, we're going to use another animation spec called decay. Now, this animation spec you can use whenever you want to simulate that decaying nature of the animation, so it gets like lower as the time goes. And the way you use it is you just create your decay, and then you just calculate the target value, which is what we're doing here. We just pass the necessary parameters, and voila. We have the position where my chip would end up. Important thing here is that we're just calculating where my chip will end up. We haven't animated anything yet. Once we have this target offset, the second step is we need to check. Is this target offset still inside the screen? If so, I am just going to let it animate until it stops, using the handy function animate decay. The third step is, like, in the case that my chip would end up outside the screen, I am going to be doing two things. First, I'm going to animate until I can, until I reach the border of the screen, and then I'm just going to animate back to the center. Important thing in here, since I mentioned animatable is coroutine-based, so it follows the same rules as a coroutine. In this case, my first step of animation is going to finish before the second one gets called. So it's important to remember that in case you want to do some synchronous thing. Cool. And that's it. As you can see, it looked a bit scary, but it really isn't. Once we have this, you already have a fling and back chip. So far, so good. But with this, I think we're good with this. And I think we're good with gestures. I think you already had a hang of it on how to do this. So let's jump into something more interesting. Let's jump into sensors. But before we start dancing with sensors, let's do a small detour and actually explain how to use these sensors. The process, because there's always a process. In this case, is again just following 3 steps. The first one is you need to pick a sensor. Of course, which sensor are you going to use? And don't worry, all of them are documented in both Android and iOS. You can just go there into documentation and pick your favorite one. Once you know which sensor you're going to be listening to, you need to actually start listening to that sensor. And as a third and last step, whenever you're listening to it, you need to actually react to that sensor event data and do something. Important thing, this sensor event is of course going to be different for each of the sensors that you're going to be listening. So for example, if you're working with gyroscope, it's going to be some rotation coordinates. But if you're working with like a temperature sensor, you're going to get some temperature information. So it's important to know how the sensor is going to work and which information you are going to get before doing anything. Cool. But how are we going to be actually doing all of this in code? What is going to be the plan? Since I mentioned at the beginning, I'm using Kotlin multi-platform. So the first step is I need to define a multi-platform sensor manager. And because it seems that Android and iOS are different platforms and they use like sensors differently, I will need to create an Android sensor manager and an iOS sensor manager. Cool. So let's translate this into code. The code for my multi-platform sensor manager will be pretty straightforward. I just need an interface. This interface is just going to have two methods, which is going to be the register listener, which you're going to call whenever you want to start listening to a sensor, and the second one, super important, on register all. Now, important thing in here is that sensors are pretty expensive battery-wise. So if you're like done using your sensor, you need to be careful to register to them, because if not, your users are going to be really unhappy that you're draining their batteries. And they can know it's you. Once we have this interface, the next step is create an expect function, which is going to be the one in charge of exposing this multi-platform sensor to my multi-platform code. Once we have this expect function, we just need to create the actual functions for Android and iOS that are going to providing the specific Android sensor manager and iOS sensor manager implementation. Of course, if you're already like working in a fancy project with dependency injection frameworks, you can use that instead of this. But for a simple project like mine, just using actual and expect works. But let's take it a step further, and let's actually see how to create this Android sensor manager and iOS sensor manager. And let's start with Android. Now, in the case of Android, whenever you're going to start working with sensors, the first step you need to do is get a reference to your sensor manager. The real Android one this time, not the one that you are creating. This is a system service, so you just get it as such. And once you have the reference to that, whenever you want to register a listener, you need to again do two steps. First, you need to check if there's actually a sensor of the type you want, because not all devices have all the sensors. And once you have that sensor reference, you just attach a listener to it. And that's it. With that, you're already going to start receiving these events. Now, whenever you're done, when you want to register all the listeners in there, you just need to go over all the listeners you registered and unregister them in the sensor manager. And that's it. I'm, of course, omitting some of the code. So if you want to see the full implementation of this, you're invited to check at the repository. But the gist is that you get your sensor manager, you get your sensor, you start listening to it. When you're done, you register. Easy, right? Cool. Let's see how iOS does things. Now, one of the main things I noticed is that in contrast to Android, where you only have like one entry point for sensors, which is the sensor manager, for iOS, you're going to have a different sensor manager depending on the type of sensor that you want. So for example, if you want some motion-based sensors, you're going to use a motion manager. If you're going to use like some activity sensor, it's a motion activity manager. If you want to use something like ambient light, you need the sensor reader, which, by the way, is part of SensorKit. And if you want to use this, you may need a paid Apple development account, because you need to change some permissions and provisioning profiles. But I digress. Anyway, once you have all your sensors managers in place, whenever you want to start listening to them, you are, of course, going to need to check which type of sensor you're asking for, and depending on that, you're going to do something slightly different. And it may look like a lot, but at the end, they're going to be same-ish. So let's see an example. Let's see the star accelerometer updates. In order to start listening to this sensor, you're going to be doing, again, two things. First, you're going to see if this sensor is available to you. And if so, you're going to start listening to those events. That's it. Same as Android, right? Cool. Now, once you're done with all of this, you're just going to register. And in this case, since I have different sensor managers for each of them, you're going to basically unregister to all of them. There are some optimizations that you can add, but for the sake of just this making it work, they should work. Cool. But that's it. It may be lengthier, and it may have more words, but at the end, it's the same. You get your sensor manager, you check if there's a sensor. If so, you start listening. If not, you're done. That's it. Cool. But with this, I think we're done with the multi-platform sensor manager. Let's go back to dancing. And let's do a rotation shift. Again, we're going to answer our 3 questions. What, when, and how. In this case, we're going to be changing the rotation of my chip. When? Whenever my orientation changes. And how? I am just going to basically replicate the same rotation as the device in my chip. Cool, right? Well, not quite. As I mentioned, we need to add a 0 step to this. And that is that we actually need to understand what type of data are we going to be receiving. So let's just do exactly that. In this case, as I mentioned, we want our orientation sensor data. So let's jump into Android. In this case, if you jump into the documentation, you're going to find that you're going to receive 3 values. Azimuth, which is the z-axis rotation. You're going to get pitch, which is the x-axis rotation. And you're going to get roll, which is the y-axis rotation. Cool. Now let's jump into iOS. If you get into documentation, you're going to find that you're also going to get 3 values, which are going to be yaw, again, z-axis rotation, pitch, x-axis rotation, and roll, y-axis rotation. If we put them side to side, we can see they're pretty similar, but not quite. There are some differences in the axis values, and there are also some ranges changes, but don't worry, we can still work with this. Whenever you find yourself in this discrepancy, and this is general, not only for sensors, the strategy is pretty simple. Just pick one as your source of truth and map the other to it. Which in my case, since I started with Android, I just decided to map to Android. Cool, but how you do this in code is pretty straightforward. The easiest way is to just create a shared data class that is going to represent your orientation, which in my case will look like this. It's basically just having azimuth, pitch, and roll, and there are some helper methods to make it degrees, but that's it. I am just going to need to, whenever I receive an iOS value, to map it to this. And since I don't want to be doing that mapping every time I'm listening to these orientation things, you can just create another helper function in your interface that is going to already do the mapping for you, and is going to let you know whenever an orientation change happens. Cool. But I think that's enough of this theory. Let's go back to our rotation shift step. And an initial implementation, why he's not changing again? There you go, cool. An initial implementation will look like this. Again, we need to define our properties, which is in this case our x, y, and z axis rotations values. Then we're going to again set up in our graphic layer. Remember to use graphic layer. And then at the end, the only thing we need to do is to start observing to these sensor manager updates. We're going to get a reference to my sensor manager. We're going to start observing these orientation changes. And whenever these orientation changes happen, we need to update each of the axes in there. Important thing here is that in comparison to the other animation that we had, in here, I'm launching each of these updates in its own coroutine. And that is why I want all of these updates to happen at the same time. I don't want X to happen and then Y and then Z. I want all of them to happen at the same time. So each of them in a coroutine. Once we have this, we're again doing snap to because I don't want any delay. And we're just passing the orientation values. And that's it. Now, small warning here as well is another small step that you need to do is you need to be careful about which units are your values on. So for example, in this case, my sensors are usually returning my values in radians, but my UI expects degrees. So just make sure you're mapping correctly your things. If not, you're going to see some wonky stuff. Cool. But with this, and that's, again, all of the code, minus the motion manager one, you have a rotation shift. Cool. And that's it for this one. Which, by the way, a small parenthesis here. If you're wondering what am I using there, this is nothing more than the virtual sensor in Android Studio. You can find it easy in the settings of your emulator, and it doesn't only provide rotation and move values, it also have other sensors like temperature and ambient light and other things. Important thing, this is Android Studio, If you want to do this on iOS, I tried to find some alternatives, but I didn't find any in the emulator. There are some libraries you can implement, but I think it's easier to just get a real device and test it there. Cool. But with this, let's jump into our last step, shake it. Again, we're going to answer our questions. What am I going to be changing? Rotation, translation, and scale. Whenever there's a device shake. And how? Well, I just wanted to do a side-to-side roll and then a little wiggle. And that's it. Nope. We again need to understand our sensor data, which in this case is going to be the acceleration. So let's just do that. Let's jump again into Android, and let's check the documentation, where we get, again, 3-axis values, but in this time, it's going to be the acceleration. Cool. Let's jump into the iOS side. It's, again, we're going to get, again, our 3-axis, and it's going to be acceleration again. We put them side to side, and we can see that they're exactly the same. Great. I don't need to do anything else. I just need to start listening to them, and that should be fine. So let's jump into Shake It again. The first step, as always, we need to define our properties, which are the ones we're going to be animating: scale, rotation C, translation. We define them in our graphics layer, and then we start listening to our sensors, which in this case, we're going to be listening to acceleration, in which each event, we're going to receive the acceleration in X, Y, and Z. Now, here is when I need to detect our shake motion. And you can do what I do usually in these cases, which is just search around and see if someone smarter than me already did something, which in this case, it did. So the only thing I did was translate that into Kotlin. And since you shouldn't just copy-paste random code in the internet, let's try to understand what is happening here. The first step is we're just calculating the magnitude of the acceleration vector, which is nothing more than, Pythagorean checks, blah, blah, blah. We get the acceleration vector. The next step is there's going to be applying a log-cut filter, which is just fancy words of like cleaning your acceleration readings, which is just going to remove some of the noise of really low acceleration changes. Once we have that, we're going to do a magic number check, which basically the higher this number is, the harder you will need to shake your device in order to the shake be detected. If you're higher than this number, it means that you are shaking. If it is lower than that and you were already shaking, this means that you stop shaking, right? And there, in that shake ended, is where I want to do my shake move. Important thing here, as you can see, sensors can be used 2 ways. You can use it as a straight source for your animation, like we did with rotation, or in here, we're using just that sensor reading as a gesture in order to trigger an animation. So this animation doesn't actually need any parameter to be inputted because I'm just going to do whatever I want, which in this case is that little roll side to side. Now, how are we going to be doing this? We're again going to be triggering each of the animations separately in its own coroutine. And whenever you see this kind of like side to side or really specific animation, you should start thinking about keyframes. So that's what we'll do. We'll use define some keyframes. But important thing in here, I don't want my animations to they're independent, right? I don't want one to finish before the other. I want them to be aligned. Whenever you find yourself in this situation, a really easy trick, if you're lazy like me, is just make sure that all of them have the same duration. That ensures that each of the animations are going to start and end at the same time. And of course, you can do this better with some transitions and add more code, but this works. Cool. And that's it. This is how you would do this shake it animation. But for the sake of completeness, let's take a look at how this keyframes animation spec will look like. All of them will look pretty similar. The first step is, of course, defining the duration, which, as we saw, is going to be the same for all of them. And each of the extra lines that you see are going to be the keyframes I'm defining. So in this case, when I'm on 0, I want the rotation to be 0. When I'm 20% already from the animation, I want it to be 180. When I'm again at the center, I want it to be at the middle of the animation, the other side, and then back. That's why my target value is also 0. So that's it. You're going to have something pretty similar for my scale and my transition. And just running that, you kind of have the shake it animation. But we're missing that end wiggle, right? Don't worry. In order to add that end wiggle, the only thing you need to do is add more keyframes. In this case, you just need to make sure that these extra keyframes happen in the same coroutine as their already previous animation. So first, you finish doing the big one, and then you do the little wiggle. But that's it. Whenever you grab all of this, add it inside your animation, and run it, and you're already going to have Shake It. If I manage to shake it hard enough. But with this, I think we're done with Shake It, and with this move, we already have them all. You can already tap it, you can already shake it, you can already fling it, and you can already ship it. But you don't need to stop there. You can create your own steps. You can create even more, like spin it, pick it, dim it, step it. Just grab your favorite gesture, grab your favorite sensor, and then just, plug an animation to it. That's my excuse anyway. But for now, I think that's it. So thank you. If you want to learn more, sorry, I'm still showing things. Yeah, I was going to show a little bit more, but anyway, if you want to learn more, I highly recommend you play around with the code. It's publicly available through that QR code. I also recommend to take a look at the Rebecca Frank's Practical Magic with Animations video, and of course, take a look at the documentation, because that's the source of truth. But for now, for real, thank you.